Hey there everyone, welcome back. We are going to continue on with our lessons on fluids. This lesson we're going to take a little shift, whereas up until now we've been talking about static fluids, hydrostatic pressure, that sort of thing. And just a reminder that what we mean by that is we're talking about the pressure inside a fluid because of depth. And we recognize that the deeper we are in that fluid, or maybe the deeper that fluid gets, the higher the pressure is because of the weight of all the fluid on top of it. For the next couple lessons, we're going to talk about fluid dynamics, which is going to really relate to the flow of particles. So you can think of water flowing through a pipe, that sort of thing. In order to do this, we need to make a simplified model. So like we often do in physics, there are lots of complicating factors. And when we talk about fluid mechanics, we're going to talk about a slightly simplified version of that. And that's just because the mathematical tools that we have are only going to allow us to think of it to a certain level. So the first thing we're going to say, the first assumption we're going to make is that the fluid is incompressible. Now we talked about this in an earlier video, which is that some fluids, like liquids, are incompressible or virtually incompressible, meaning their particles can't be squished any closer together. Some fluids are easily compressible, like gases. We are going to deal with, when we talk about dynamics, we're going to assume that the fluid is incompressible. So we're going to mostly be talking about liquids, or we're going to make a big assumption about the gas, which may or may not be totally true. The second thing is that the fluid is non-viscous. Now, when we say non-viscous, what we mean is that when the fluid flows, there is a negligible resistance to flow. This idea of viscosity, you might think about if you have, for example, like a jar of honey and you go to pour it out. Honey is very viscous, and so it's going to just internally, it's going to resist a certain amount of flow. Whereas if you have a jar of motor oil and you tip it out, it's going to flow very easily because it's relatively non-viscous. This is a little bit like in the early days of your physics education, you probably talked about frictionless surfaces, and this is very much along those same lines. So we're going to deal with non-viscous, non-viscous fluids. And the last one is that the flow is steady. And what I mean by that is just that as the fluid flows, there's going to be no appreciable changes in either its density or its flow rate. So the density stays the same. It's not like you're going to have, water flowing through a pipe and all of a sudden that turns into tar or something like that. And at the same time, that the flow rate, you turn the tap on and it just flows at a constant rate. So the flow rate is also constant. So with that in mind, let's talk about flow rate. We're going to get a couple of new terms this video, and this is the first one. So flow rate really refers to how much material is flowing through the pipe at a given time. If you take an example like this pipe right here, if I was to look at one cross-section of the pipe, and I was to count the particles that are flowing past that point. Okay, how many particles are flowing past this per second? That would give me an idea of the flow rate. So what we're going to say is it's going to be the volume of fluid that flows past a particular point in the pipe over a given time period. So you could imagine our formula for flow rate is going to be F equals V over T. Now there's a couple of things we need to be aware of there. The first is that this V here is very much volume and not velocity or speed. And we're going to see that in a moment because, of course, if these things are flowing, then they have speed. So it's capital V for volume. And a reminder that in physics, we're going to measure volume in cubic meters. So not liters like you might in other courses, but in cubic meters. And just as a reminder, 1 cubic meter is equal to 1,000 liters. So just kind of keep that in mind if that gets thrown at you. So let's talk about something called the equation of continuity. So if I have a tube and fluid is flowing into one end and out the other, you could imagine that as it flows, it might change shape. So it might be wider in some points or narrow in others. It might go uphill or downhill or whatever might happen. But just recognize what happens in this example here. If I change the shape of this pipe, and I'm just going to squish this down here because this is kind of fun. Okay. Now, notice that I haven't really changed the height of the pipe, but something has very much changed. If I put some dots through here, we can follow these dots as they go. When they're going through the wider portion of the pipe, they kind of move their way along, and as they get to the narrower portion of the pipe, they're going to change. And what changes pretty clearly is their speed. Okay, so as they get to that narrow portion of the pipe, they're going to speed up. Now you can think about this. If I was to measure these two, so here I've got a speed of 1.6, and then in this narrow portion here, I've got a speed of 6.4. So not only do they speed up, but they speed up quite a bit. Just by kind of chopping the pipe in about half, I seem to have increased my speed by a factor of 4. So that made a really big difference. This is probably something you've experienced if you've ever had like a garden hose and you put your thumb over the end, then you can actually spray a really far distance because you can actually speed up the velocity of the water coming out of the hose just by changing the area that it has to flow through. The equation of continuity tells us that the flow rate through a pipe is constant at all times. So flow rate is constant at all points in a closed tube. And this should sort of make sense because if we've got fluid flowing into the tube and it's not compressible and the tube isn't leaking, we're not losing any fluid, then whatever flows in has to flow out. And so this kind of explains why when we get to a narrower section of the tube, well, then it has to speed up in order to get that same amount of fluid flowing through that segment of the tube. So one way we can, we're actually going to derive a formula here using this basic idea. What I want you to do is picture this tube, and I'm going to picture a slug of water, and a slug of water or fluid is just like a little cross section, a little like slice of fluid in this tube. And you can see that the fluid is flowing in here to the tube and it's coming out of the top. Now, this same slug, when it reaches the top, as you can imagine, is going to look like this. Because of the smaller area, it's going to be spread out over a longer length. So we can define some variables here. So you can see I've got area 1 at the bottom and area 2 at the top. And I've got length 1 at the bottom and length 2 at the top. And so one thing we notice is that length 2 increases as the tube gets narrower. But what has to be true is that the volume flowing through here has to stay constant. So for that single slug of fluid, if the flow rate has to stay constant, then the flow rate through point 1 has to equal the flow rate through point number 2. And since we know that flow rate is volume over time, volume 1 over time has to equal volume 2 over time. Now, you might be tempted to cancel out those T's and see where that goes, but just hang on to them for a second. Think about that slug of water. The volume of that slug of water, the volume there is going to equal the cross-sectional area times the length. So of the cylinder, right? So I could rewrite this whole thing as saying area 1 times length 1 divided by time is going to equal area 2 times length 2 divided by time. And this is the key insight right here, that I've got this little thing here, length over time. Well, what is length over time? If you think of how fast this slug moves through the pipe, well, the speed that it moves at is just the distance divided by the time. Again, if it's going at a constant rate. But the distance traveled really is the length of the slug. So I could say that the speed is the length of the slug divided by time, which means this length over time is really referring to the speed. And so what I get is I get an equation that says A1 V1 equals A2 V2. And this is the part where you got to be careful because these V's are speeds, okay? So in the previous example, that was volume, and in this case, it's speed, and I'm sorry, that's just the way it works out. But this should sort of make sense because really what this is this is just another way of stating the law of conservation of matter, that whatever flows into the pipe has to flow out, and we can't compress it at any point. So really, this is just following the law of conservation of matter. Okay, so let's see how this plays out in a couple of examples. I've got a garden hose with an inside diameter of 16 millimeters. The hose can fill a bucket of 10 liters in 20 seconds. What is the speed of water out of the end of the hose? Okay, so I'm just going to draw a diagram here. So I've got a hose like this, okay. And the diameter of the hose is 16 millimeters. So that's 0.016 meters. That's my diameter. Now, one thing to keep in mind is we're often talking about areas. And if we're talking about areas, then I don't particularly care, or I don't usually care about the diameter. I usually care about the radius. So it's often a good idea to just write down the radius while you think of it. Now, the radius is going to be half the diameter. So 0.008 meters is going to be my radius. Okay, so we know that it can fill a 10-liter bucket in 20 seconds. So basically the question is just asking how fast is water flowing out here? So what is the speed of the water flowing out the end? Well, I know that flow rate is equal to volume divided by time. So this is just going to be my volume divided by the time. Now recognize this is 10 liters, and 10 liters is actually 0.010 cubic meters divided by 20 seconds. So my flow rate works out to be about 5.0 times 10 to the negative 4 cubic meters per second. Now I want to find the speed. Now recognize that flow rate also equals area times speed. So that means that the speed is just going to be the flow rate divided by the area. And don't forget that the area, I'm going to assume that this is a cylinder. So the area, the cross-sectional area will just be pi r squared. So the flow rate of 5.0 times 10 to the negative 4, all divided by pi times, and use the radius, not the diameter, 0.008 squared, should give me a final speed of about 2.5 meters per second. Okay, and there we go. Now, the follow-up to this question says, okay, so in this last example, what diameter of nozzle would cause the water to exit with a speed of 4 times greater than the speed inside the hose? So I've got the water's flowing at 2.5 meters per second, and then basically what diameter would I need to use to get it up to 10? Now, you could just solve this using numbers, but I'm going to try and kind of work it out proportionally instead. So if I put a nozzle on the end of this hose that kind of tapers down like this, okay? And so I go from a certain diameter, a certain radius here, R1, and I end up at a new radius R2. I know that if I want the water to go faster, then I'm going to need a smaller radius on the other end. So let's think about this. Our equation of continuity tells us that A1 times V1 has to equal A2 times V2. And what I'm looking to find, what I'm hoping to achieve, is that my V2 is going to be 4 times V1. So I can rewrite this second equation here to say, okay, I want A1 times V1 to equal A2 times 4 V1. And so actually my V1s will cancel out. And essentially what I've got is I've got A1 has to equal 4 times A2. Now, since the area is pi r squared, I can say that pi r1 squared has to equal 4 pi r2 squared. And again, my pi's cancel out. And the last thing to notice here is that I can actually set up a ratio that basically says that r1 squared over r2 squared has to be 4. So the ratio of r1 to r2 squared has to be 4. And that's a key insight, is that because the radius is squared, then it's going to have a larger effect on the overall speed. So I can take the square root of both of these sides and say that the ratio of r1 to r2 should be 2. So there's my answer, is that I would actually only need the nozzle to be half the size of the original in order to increase the speed by 4. And this is what we actually saw when we looked at this very first demonstration here, is that by changing the diameter or the radius by a factor of 2, I actually increase the speed by a factor of 4 because I changed the area by a factor of 4. Okay, that is it for our lesson on fluid dynamics.